Well, good morning to all the Science Circle. Um, this is Patio Plasma, and in real life, I'm a physics professor. And so excuse me while I take a little trip into chemistry and talk about the science of nail polish. So I start out here giving you some inspiration of where women and men paint their nails with a little bit of chemistry and astronomy. But that's not the science I'm talking about. What I was thinking was about the actual chemistry of some of the different nail polishes. And the main ingredient in classic nail polish is nitrocellulose. That happens to be the explosive ingredient in gun cotton. It's quite flammable. And it's dissolved in various solvents like ethyl acetate, also flammable. And it includes pigments and other ingredients. So you paint on the nitrocellulose containing solvent onto your nails. It evaporates and cools your nail. And the nitrocellulose, it's a long chain polymer molecule which lies down flat against the nail, making it smooth. Okay. Yes, the lecture's in voice with words. So here's a little look at the nitrocellulose molecule. It is a long chain molecule. These monomer parts of it link together. And of course, it's the main ingredient in plants, like cotton. And it can be then combined with nitric acid. And the nitric acid results in a combination called nitrocellulose. This was discovered when a chemist dropped a cotton rag into nitric acid accidentally, wiped up a nitric acid spill, and while he was drying the rag, it burst into flame. So, it's rather interesting history there. So here's a picture of the small molecules. Ethyl acetate, it is a tiny molecule. It has a high vapor pressure. It's liquid, but evaporates very quickly. The nail polish also contains butyl acetate, and when they evaporate, they give you the aroma of nail polish, which is reminiscent of ripe fruit, I believe. And in this model, the blacks are the carbon, the reds are the oxygen, and the whites are the hydrogen, same as in the last one. Oh, this gets better, Mary. Wait till you hear some of the other ingredients. And of course, one of the most important additions is the coloring agents. And these are pigments. They absorb some wavelengths of light and reflect others. And they're solids held in suspension in the liquid. And when the liquid evaporates, the solids are left behind with the nitrocellulose giving it color. And for example, the black is made of carbon black. And I think even in the audience, we have an expert about making carbon black and grinding it down to very small particles. And one of the big problems was keeping the colors in suspension. You have a bottle of nail polish and you don't want the color particles to settle to the bottom in a year or maybe even 2 years. And so that's a really tough problem and requires a lot of grinding. Yay, Charlize. So for example, a pigment might be manganese violet. Now some of these pigments are really small molecules, and they actually, when they go into the solvent, they dissolve. instead of remaining as a particulate. And the molecules themselves then can penetrate your nail and leave it colored when the rest of the nail polish is removed. And some of the worst offenders, if you look at the ingredient list, DNC reds numbers 6, 7, and 34, and FDNC yellow number 5 lake. So if these are components in a nail polish you're using, you might discover that your nail itself has been dyed for quite a long time afterwards. So you better be careful. We're going to talk later about using a base coat. And so putting down a base coat, a clear, transparent base coat, can protect your nail from staining. Oh yes, and indeed, many of the ingredients in nail polishes can soak into your regular nail and have it turn yellow. So here I am at the Exploratorium, and showing the full spectrum here, from right to left: red, orange, yellow, green, cyan, blue, violet, and then ultraviolet, which I show as black. And at the two far ends, I have extra red, meaning to be infrared, to get the full spectrum. Yeah, I did these nails myself. So in 1920, they finally made automobiles not black. They patented car paint. And then in 1921, with pretty much the same recipe, patent was taken out for nail polish. Yvonne Milner, in 2010, reversed the process, and she's painting her entire car with nail polish. So took hundreds of bottles of nail polish, even to get it coated as much as you can see here. Well, when I talk about something besides nitrocellulose and solvent and pigment, there are many other ingredients. Just look at this list for Zoya, which is one of the nail polishes that's higher end and tries to be conscious of health issues. And in fact, there's a group called EWG that gives a score for makeup products, which lets you find out how dangerous perhaps it is. And a score of 2 to 3 is mid-low for its ingredients. But look at the names of all these ingredients. You really do have to be an expert chemist to make nail polish work. So, for example, one thing they add is an adhesive polymer, tosyllamide formaldehyde resin, with the emphasis on resin. Think about tree resin and how sticky it is. And that particular chemical adheres to the nitrocellulose and to the nail. It also penetrates the nitrocellulose, goes between the nitrocellulose molecules, making it less brittle so that it can bend a bit when your nail bends without popping off. In addition, to make the, so it says formaldehyde, but this formaldehyde is not in the gaseous form. This formaldehyde is bound in the tosyllamide and the resin, and in that form, it does not penetrate your nail, and it doesn't go into the gas form. So it's like sodium chloride. You know, that sodium is nasty stuff, but in sodium chloride, it's necessary for life. So even though the word formaldehyde appeared here, don't jump yet. And plasticizers, plasticizers like camphor, it's a molecule that fits in between the polymer chains and makes it more flexible. And we'll learn about another plasticizer, dibutyl phthalate, which has been removed from many nail polishes because it's considered a slightly dangerous chemical. But camphor, not a problem at all. And as Charlize will say, one of the things they add to nail polish is clay, in particular steralconium hectorite. And the clay changes the viscosity. Look at the chemical formula for this stuff, man. And by making it thick, it keeps the molecules, it keeps the particulates, I should say, in suspension for a couple of years. And there's an interesting property to this clay. It's somewhat thixotropic. One of those great words, thixotropic. I love to say that. And thixotropic is a description of ketchup, which is in the bottle, it sits there and it's kind of very thick and doesn't flow very well. But if you vibrate it or stir it a bit, it becomes liquid and flows. And then after it hits the hot dog, it stops flowing. So that's what we want for nail polish. So as you add in the clay and other molecules to the nail polish, you change its viscosity. Low viscosity runs like water and high viscosity flows like honey. But you also want it to have this property called shear thinning. And that means when it's stuck on the brush, it stays there. When it's liquid on your nail, it stays where you put it. But when you brush the liquid onto the nail, that's shearing it, that's spreading it, it becomes a liquid and flows and makes a beautiful level layer. And so there's a lot. This is actually physics, but we have to use chemistry to achieve the physics of low and high viscosity and thixotropic shear thinning. Who knew that all this science was in nail polish? By the way, there's one big source of steralconium hectorite clay in the world. It's the Hector mine, and it's near Barstow, California. And one of the problems you might have noticed, if you remember that chemical equation, was that hectorite has a lot of lithium in it. And right now, lithium is being used in tremendous number of batteries. So our supply of hectorite for nail polish, although I think there are cubic miles of the stuff, is being slightly reduced by our demand for high-power batteries. That's right, the prices are going to go up. So here's a modern nail polish, and we'll review all the ingredients. Oh, that would be great. Recycle batteries into nail polish. The ethyl acetate and butyl acetate, the solvents, nitrocellulose, the polymer, isopropyl alcohol, another optional solvent, polyester resin, a resin to adhere it and coat the particles. Dibutyl phthalate probably wouldn't be found in the most modern nail polishes. That makes it elastic, makes it plastic. Styrene acrylate copolymer, again, makes it smooth and shiny. And there you see steralconium hectorite and bentonite, those are the clays. Benzophenone 1, it's an ultraviolet protector to keep the nail polish from changing color when it's exposed to ultraviolet, and an optional fragrance. Oh yeah, you know, when I paint my nails, I'm always in a good mood. Oh wow. Yeah, it's interesting. If you go to Sweden, you find all the barns are painted the same red. And it just happened to be a byproduct of iron production. It was an iron oxide that they made into paint, which now is the classic color of a... oh yes, and I saw the edible nail polish, and the nail polish that smelled like Kentucky Fried Chicken. Yeah. Okay, so in addition to the main colored nail polish, very often you can use a base coat. And this is the first layer you put on, and it's really designed to stick to the nail and to nitrocellulose. And the base coat has a lot more plasticizer in it, so it's really flexible. It has a good amount of solvent, so it dries quickly. You can use it to protect your nail from staining pigments, and some of them have more clay in them, or talc, which fills in the ridges. And so in the bottom picture here, let me try something here. On the bottom picture, I've got my laser on. The left one with the red dot is a normal ridged nail. And just like Leslie was mentioning, this one is yellowed at the tip. And then in the second one here, this is after a ridge-filling base coat has been applied. And then over that ridge-filling base coat, when you apply the actual nail polish, it's really smooth and shiny. I like the idea, Charlie. It's a bacon smell. Yeah. But the thing is, so if you go to get your nails done, very often they'll buff your nails down. They'll sand down the surface of the nail to make it smooth. But many of the nail experts discourage sanding your nails and buffing your nails. They point out that these ridges, the high parts of the ridge, are actually the healthiest part of the nail. And when you remove those, you leave behind just the grooves, which were the thinner part of the nail. So you're thinning your nail. And so instead of getting smooth nails by sanding off the nails you have and making them thinner, the modern suggestion is use a ridge-filling base coat or use a base coat. And that will be better for your nails overall. And there's also by the way, the base coat and the top coat, they can be formulated without all the extra inclusions that are needed to keep a pigment in suspension. So the base coats and the top coats can be made to be very shiny and to dry really quickly, and also to be flexible. So they can be designed to really work well at the role they fill, whereas the actual nail polish itself is a compromise in order to get that color. So the top coat, you want it to be really hard to protect the colored part from scratches. You want it to be shiny, although some of them are matte. And you'd like to have them dry fast, but you have to realize that you get a thicker, a more viscous top coat. It's shinier, but it dries more slowly. And many of the women here know that to really dry a nail polish, it can take a couple of hours before it stops being really soft and susceptible to being scratched or poked. At least the classic kind of nail polish I've been describing so far. And of course, we have to get the nail polish off again. And nail polish remover is usually an acetone. And the acetone is a solvent molecule that goes right in between those nitrocellulose molecules, puts them back in suspension, and removes them from the nail. There are non-acetone nail polish removers. They're usually based on ethyl acetate and butyl acetate, the actual solvents that are used in nail polish itself. Acetone is very drying, and so it will dry out your skin and dry out your nails, and dry nails are susceptible to breakage. So you really have to be careful with not overdoing the nail polish remover. Yeah. Okay, so there's been a modern revolution in nail polish. Instead of using nitrocellulose and solvents that evaporate, we actually use gels, a thick gel that which is based on a methacrylate polymer. It actually starts out as a monomer, and it's turned into a polymer by the application of ultraviolet light. And these are really smooth and shiny, and they dry in just 2 minutes. Instead of having to wait 2 hours before the nail is hard, that takes 2 hours. But the modern ones are called soak-off, and they require a 20-minute soaking in pure acetone to get them off. And that can be extremely drying for the nail itself. So there's a little bit of problem. So here's the chemistry. So we start out with a bunch of these blue dots, which are called monomers. And there's a photosensitive catalyst, which is shown here as this double molecule. When ultraviolet light hits that photosensitive component, it breaks it into two parts, each with a free electron. That little dot is a free electron, and that's called a free radical. And those molecules, those free radicals, can react strongly with other molecules, and they can cause damage in your body. If you get free radicals in your body, they can break down other molecules and actually cause some damage. But in the nail polish, what they do is the free radical with its electron combines with a monomer, binds to the monomer, but it still has a free electron. And then it hits another monomer, and the chain continues. So it adds monomer after monomer after monomer until I get a long chain polymer. And this goes on until perhaps it meets another long chain polymer. And look at this, you have two electrons looking for a partner. Electrons like the paired relationship. And so they pair up, and then I have a long chain polymer. And so in a modern nail polish, the monomer might be ethyl methacrylate. In earlier gel and acrylic type polishes, it would be methyl methacrylate. But methyl methacrylate has been taken out more recently and replaced with ethyl methacrylate, which is slightly safer to use. So in the old days, there were acrylic nails and hard gel nails, as they're called. And these monomers had side branches on them so that they could cross-link and make a rigid three-dimensional structure that could not be dissolved by many acetones, or very difficult to dissolve. Modern soak-off gels is what they're called. Soak-off meaning they will dissolve in 100% acetone. They have longer monomers, less cross-linking. And so that's really something to keep in mind when you're looking at a more modern nail polish. The gel reaction, when you expose you coat your nail with the monomer and the photoexcited molecules, and you hit it with ultraviolet for 20 seconds to 2 minutes, the reaction, the polymerization reaction, is exothermic. And so it heats up your nail. And some of the earlier ones, the hard gels, some people's nails would heat to 150 degrees Fahrenheit. And sorry about those of you that speak Celsius. But that's way up in the, 50 Celsius range, which is really hot. You don't want that. The modern ones have been toned down, and you do not want a really burning hot feeling when the nails are curing. And when they polymerize, they shrink 2 to 20%. And a 2% shrinkage is not bad at all, but a 20% shrinkage, look at this, the nail polish has pulled back from the edge of the nail and leaves this white line. And in the 20% case, it'll actually pull back from the edges as well. So you're really, a really good polymerizing nail polish will not shrink that much. And if you've ever had this done, you might notice oxygen in the air interferes with the ultraviolet cured bonding at the surface. So that interference creates what's called an inhibition layer where the polymerization can't happen. And when you're done with the curing, you get the sticky layer. It's like gummy sticky on the top. And you have to remove that using isopropyl alcohol, and that leaves behind the beautiful, smooth, cured gel nail, which will often last for 2 weeks. So these nails are cured with ultraviolet light, and the photoinitiator, that's that photosensitive molecule. And they're designed to take some wavelength between 400 nanometers and 315 nanometers, and that's in the ultraviolet A portion of the spectrum. The ultraviolet comes in like 4 ranges: ultraviolet A, ultraviolet B, ultraviolet C, and vacuum ultraviolet. And the ultraviolet C is germicidal. That's used in hospitals and in water purification facilities. And it's nasty ultraviolet. Ultraviolet B is in sunlight, and that gives you sunburn. It has enough energy. Those molecules have enough energy to break apart the DNA in your cells and can, with large exposures, lead to skin cancer. Ultraviolet A can also break bonds in your DNA. It's less damaging than UVB, but more penetrating, because the UVB reacts so strongly it doesn't go deeper into your body. The UVA interacts less strongly, but it goes deep. And so it was a great breakthrough in sunblock when they made broad spectrum sunblock that would block the ultraviolet A as well as the ultraviolet B. And to tell you my own personal story, I come from Irish ancestry, and so I have very little melanin in my skin in real life. And so the first hike I would do every spring, I would get sun poisoning, even though I wore sunblock. And the sunblock was blocking the ultraviolet B, but it was letting through the ultraviolet A, which was breaking down enough molecules that I was poisoning myself with sunlight. With modern sunblocks, that does not happen. I am so happy for the invention of broad spectrum sunblocks. So you see, you can come to these lectures and learn more than just about nail polish. So back to the gels and the acrylics. So we'll start off with acrylics, and there are 2 different kinds. There's methacrylics, or ethyl acrylics, and the acrylates. And the hard UV gels are the acrylates, and those cannot be soaked off. If you want those off, you have to grow them out over months or grind them off, and that can really damage your nails. So those are a long-term commitment. The original acrylic nails were a combination of 2, a solid powder and then a liquid, and that liquid help the polymerization happen. Those are called acrylic nails, and they could be soaked off with a lot of acetone. And oh, that's interesting, Baragon. I'm sure that some acrylics are, but recently in the nail industry, they've really gone over to the ethyl acrylates, which are less damaging. And the newer ultraviolet gels are over here. And they're called soak-off gels. And with 20 minutes soaking in pure acetone, they will come off, drying your nail plate, but they actually do come off without damaging you too much. Oh yeah, the acrylamides, right? Yeah, you don't want the acrylamide gels. Okay, so for example, here's the formation of an acrylic nail polish. And if you follow the bouncing electron, which is the asterisk here, so we have our photoinitiator on the left, which absorbs an ultraviolet photon and gets excited. There's the electron. And that electron comes over, and here's the monomer. There it is. And look, watch the double bond. Okay, over here, the photoactivator hits the double bond is gone. It's a single bond with a free electron right here underneath. That's the free electron. And then that now photoinitiator monomer hits another monomer, and it's got that free electron, which goes over and breaks the double bond and stacks up 2 of them together with a free electron. And this goes on and on and on and on until you run out of monomers. The monomers themselves, you do not want them left behind. Many people are sensitive to the monomers. They're small enough molecules, they can penetrate the nail, they can get on your skin. People have allergic reaction to the monomers. And so in the nail polishes, they want to design them so there's no leftover monomers, that there's enough photoinitiators that all of these monomers are taken care of. They all go into the polymer, which is so long and so strong it can't penetrate the nail. Yeah, what's the color of an electron? Right, and you don't want any leftover initiators either. How great, Mike, I'm glad you're here. I had the initial disclaimer that I'm a physicist talking about chemistry. So take everything I say with a grain of salt. All right, so here's the monomer. It's look at the initiator, the free radical, the monomer with the double bond, and then the radicalized monomer, where we see that free electron just waiting to go on. And here, for example, is the photoinitiator, hydroxycyclohexyl phenylketone. And this molecule absorbs, as you see here, 240, 280, and 330 nanometer ultraviolet. So they design different photoinitiators for different wavelengths, and different companies require a slightly different wavelength range to actually cure their nails. Right, a linear chain reaction. And some of the molecules have multi-bonds, so like this one here. And what this allows is the cross-linking. Polyethylene glycol diacrylate, polyethylene glycol dimethacrylate, and acrylic modified polyvinyl alcohol. And so these molecules allow for the cross-linking, which gives a bit more strength to the nail coating. Well, recently there's been a new advance, and the advance is called a hybrid nail polish. And Sally Hansen is one of the first ones to have this. It's got a color layer which contains the oligomers, the medium length chains that are going to polymerize. And the top coat only contains the photoinitiators, but they managed to find a photoinitiator that would cure in visible light. So this does not need ultraviolet light to cure. And here's the name here, ethyl trimethyl benzoyl phenylphosphonate. And so, you know, the chemists are out there looking for all these amazing molecules that have different properties, and that you don't want it to be dangerous to people. You can't inhale it. It can't penetrate the skin. It can't poison you. And yet it has to be sensitive to visible light. Right? Yeah. Oh. So we have to... in fact, you have to go to the nail polish site. Usually the manufacturer sends you to their site in order to find out what all these are made of. And I spent a lot of time for this lecture going to nail polish sites, finding out what they're made of. So one of the things I do at the Exploratorium is I'm the senior scientist, and here I am in the Exploratorium at an evening event for adults only, doing this particular lecture on the science of nail polish. And here we are, everybody in this audience is watching nail polish dry. And in fact, the device I'm holding in my hand here is a thermal infrared camera. And I've just painted the one nail on this fan of nails red, and it's drying right now. And by the way, in this image, this is my new boss, the director of the Exploratorium, meeting Patio for the first time, and this is his wife, and they're having a good time. Yeah, it was a fun night. Okay, so here I have one nail painted. This one, for this image, I did it in blue. And then, yes, I like that, yeah. And here's nail polish drying. Viewed through the thermal infrared camera. Now, in this camera, dark means cold and bright means hot. And the image in the infrared is offset from the image in the visible. So this hot region here is actually this plastic here, and this cold nail here is actually this nail here. It has two cameras. It has a visible camera and an infrared camera, and it's meant for looking at things at great distances. So when I looked really close, the two images get offset. But you can see that regular nail polish, when you paint it on the nail, evaporates, dries, and makes the nail cool. And many of you who have done this may have felt that cooling sensation. But here was my puzzle. Oh, and this is on this nail here, I've painted this one right here with a clear coat of ultraviolet cured soak-off gel. And when I exposed it to, and I exposed it and all the other plastic nails, not coated at all, to ultraviolet light. And you can see over here, it's bright, it's hotter. It's even hotter than where my hand held the stem down here. So the ultraviolet curing is exothermic, and it made that nail hot. Well, I wondered if Sally Hansen, with its hybrid nail polish, was really telling me what was going on. So I decided as a scientist, since I had the tools in my hand, to find out what was going on with the actual Sally Hansen hybrid nail polish. So I painted the nail with the hybrid, and I put it in an absolute dark room. Okay, so in a dark room, and here is what happened in the dark room. You can see that at first, that nail polish cooled off the nail. So indeed, it does have a solvent in it at first. And then, after allowing that solvent to completely evaporate and have it reach room temperature again, I put it in the ultraviolet light source. And here you see that nail is actually quite bright. And so it's exothermic. And that tells me that Sally Hansen was telling the truth. This hybrid nail polish has both evaporation to thin down the layer, and then followed by curing. Now, I wanted the curing to happen rapidly enough that I could see an effect. So I actually used ultraviolet instead of just room light. I should probably do this experiment again with room light to see how well it works. Maybe even sunlight. So I haven't done that yet. But that's the thing about science. You know, people make claims. Scientists, experimental scientists, have the tools to go find these things out themselves. And I have to tell you, that was fun. Well, there are other chemicals that are added. Here's one of my favorites. And this is in a nail polish called CND shellac, which happens to be soak-off gel. And this has a high index of refraction. And what it does is it increases the amount of reflection from the nail polish. It's used in the top coat. And for example, diamond has a high index of refraction, so it reflects a lot of light. And so does this stuff. So this is the kind of thing that the chemists are looking for to add to nail polishes to change its effects. That's right. Oh, thanks, Mike. A kind of polyester. Thank you. Nice to have a real chemist in the audience. Well, for those of you that think about your nails, this is nail anatomy. We've got the nail plate, which is that layer of keratin. We've got the cuticle around it, which coats the edge between the skin and the nail, and the nail matrix. So over here in this image, you can see the eponychium, this E here, which is the bridge between the skin and the nail. This stuff here, this is the nail plate itself. And down here is the nail matrix, nice rich in blood, where new nail is being added on all the way here and it propagates to the right. And that nail, as we go on, here's a close-up microscopic view of the nail plate. Here's the nail plate here. You can look at the fibrous nature of that, the tiny little fibers of keratin, and the skin. And we had a very good close-up camera at the Exploratorium, a camera microscope. So we let people actually look at their nails and their skin. And those young women had really lovely looking nails and skin, but us old ladies, whew, scary. In fact, here's a real close-up, the nail. You can see these like flakes on here, the scales. So it's a translucent, fibrous keratin protein. It contains a lot of the amino acid cysteine, which has disulfide bonds, which cross-link for strength. And water goes into the nail itself. It's 10%-ish water. Oh, this is a scanning electron microscope view. And that means when you put your nails in water, they soak up the water and they get swollen and soft a little bit. And so be careful. If you're going to have nice nails, wear gloves when you're doing dishes or working with water. And don't soak your nails too much right before you do a manicure. All these little science hints. Well, there are all sorts of specialty nail polishes. Oh, by the way, that disulfide bond, if you burn nails, if your nails catch on fire, don't do that. You can smell the sulfur from the disulfide bond. So here's some of the physics that has been incorporated into nail polishes. They have little linear iron filings inside the nail polish, and on the top of the nail polish itself, there's a magnet, a patterned magnet. And when the iron filings line up parallel to the surface of the nail, they're bright white. And when they line up perpendicular so that the end of the rod is pointing to you, it's dark. So they can put patterns in your nail that look like star sapphires. This doesn't really work very well, alas. This picture is far better than I've ever achieved myself. So it takes real skill to get the thickness and the timing just right on the magnetics. It's a great idea, and maybe someday we'll actually manage to make it. It's coming up on Halloween in the United States, and so at the stores you can now find glow-in-the-dark nail polish. Ah, great. Thank you, Baragon. Boy, it's great to have chemists in the audience. Yep. Yeah, that's the problem. You want the magnet really close to the nail to line up those iron bits, but you don't want to touch it because then you scar the nail. Somehow I've got to figure that out. One of my students, so I was a physics professor for many years in the university, and one of my students went on to General Motors, where he was on the team that invented neodymium iron boron magnets. And those magnets are 10 times stronger than any previous magnets. And there are tens of kilograms of them in every electric car. So my student has helped revolutionize the world and save us from gasoline. And as a professor, that's kind of the nicest thing you can ever know, that your students went on to learn enough from you that they could change the world. So I want to use neodymium magnets and get a little distance between me and the nail polish. So glow in the dark, these have molecules in them that absorb the ultraviolet and emit visible. So in the presence of ultraviolet, your nails will glow. It's called fluorescent molecules. And it also comes in lipsticks and other cosmetics. And I like this one. Since I love lightning, and I gave my previous lightning lecture, I had to show you this one, where a woman actually did lightning bolts, but did the lightning bolts in glow-in-the-dark nail polish, so they glowed under UV. Now, there's another kind of nail polish called neon nail polish, and the neon nail polish is supposed to take the ultraviolet from sunlight and excite a molecule which re-emits it in some region of the visible. And you can tell a true neon nail polish by when you put it under dark light, under UV light, it should glow because it's absorbing that UV and re-emitting visible. And there's even another kind that's, instead of being fluorescent, it's phosphorescent. And the phosphorescent will continue to glow when the light is off. It doesn't need ultraviolet. You expose it to visible light, the chemicals absorb, they get excited into what's called a metastable state, and then they slowly drop down from that metastable state, giving off light of a lower energy than the excitatory light. So you put it in visible light, and then you go into a dark room, and your nails glow. So the difference between fluorescent and phosphorescent is fluorescent light is re-emitted within 10 to the minus 8th seconds. That's 100th of a millionth of a second. And phosphorescent light is emitted on a longer time scale than that. But phosphorescence can have a half-life of tens of seconds. So it can go much longer than 100th of a millionth of a second. They also have color-changing nail polishes. And on the left here, you see no sun, and on the right, the same nail polish in the sun. And in this case, the UV light is absorbed by a carbon atom in a complex molecule. It's got two planar sections to this molecule. And when the carbon absorbs the ultraviolet, the molecule, the two plates twist and become in one plane. And that twisted molecule is now a larger cross section and resonates in the visible and becomes a visible dye. So really nice chemistry here. And we also have temperature changing nail polishes, both in regular and in gel. And so over here, you can see that as you go from one temperature to another, the nail polish changes color dramatically. And what these nail polishes do with temperature is that they have a chemical in there that's actually changing phase. It's going from a solid to a liquid as it warms up. And in the liquid phase, it's dissolving some of the dye molecules. And by breaking up the dyes, by dissolving them, they become less reactive with light. When you put molecules together, when you put pigment molecules together into a bigger chunk, going from a single molecule to a larger one, it becomes more interactive with the light. So there's actually a phase change going on in the polish as it changes color. Yeah, and that's right. So these are thermochromic nail polishes. One of the great lectures I saw at MIT, in Playboy magazine, they actually painted an entire model with thermochromic dyes, and you could see the temperatures on her body. Of course, they used a woman. That got a good reaction from the audience at MIT. They have crackle nail polishes, and so in this case, what the person has done is they put down a white layer of nail polish and then put the blue crackle on top. And this nail polish is designed to shrink. So it shrinks and breaks, and you can see the white underneath. Oh, yeah. So I actually use this when I'm teaching geology and about how clay dries and cracks. So it's you can use nail polish while you're teaching science. That's right, Mike. It's not a bug, it's a creature. Now, near and dear to my own heart are beetles. And beetles are dichroic, meaning that means two colors, of course. And the beetle color changes depending on the angle the light is bouncing off of it to your eye. And boy, does this make for good nail polish. So my particular favorite is ILNP. And here is 3 of their nail polishes that change from a nice blue or green to an incredible violet. And really very nice. They have a nice range of colors. And of course, going back, so no sooner had chemists discovered this wonderful color-changing material, which I'll tell you about in a minute, that it was used for car paint. And so this car changes color as it drives past you. Oh, yeah. Yay, books. Yep. I love that. Welcome, books. Good to see you here. Okay. And for example, these black pieces of paper were put underwater, and then a drop of clear nail polish was put on top of the water where it spread into a thin layer. And then the black paper raised up and gathered that thin layer, which dried. And what you see here is color, but it's not a pigment color. This color is completely controlled by the thickness of the transparent layer. So what you're seeing, each color here is one thickness. This is a topographic map of thickness. And here's a little more variety in the thicknesses. Each color is a different thickness, having to do with an integer or a half-integer number of wavelengths of light thick of a transparent material. So not all color is, oh, Baragon, yeah, you probably, it might be a little hard. Yeah, that's a real challenge Baragon just proposed. Can we make a nail polish that makes an image only when viewed at a given angle? Oh, that's going to be a challenge I'll have to take up. So to make iridescence, what you need, here is the transparent layer right here. I'm oscillating back and forth on the transparent layer. And then light, which is a wave, comes in, and some of the light reflects off the top surface, and some of the light reflects off the bottom surface. And the light that went to the bottom surface had a longer path, and in addition, the index of refraction of this material is higher than air, so it shortens its wavelength, although that's not shown here. And then when these two waves come out, look, they cancel. The peak of one and the valley of the other coincide. So this particular wavelength of light will not reflect at this moment. But at a different angle, the path length might be different, and this wavelength would reflect. So to make this, what they do is they take mica flakes and they coat it with thin layers of titanium dioxide. But lately, even though mica is dirt cheap, it's kind of yellowish sometimes. So they are now using synthetic mica, fluoroflogopite, synthetic mica. So take a look at this wonderful chemistry here of the human synthetic mica, which they coat with titanium dioxide to make these wonderful effects. And so in nature has discovered this. So we have abalone shells. And abalone shells are actually made, when we look at them with a scanning electron microscope, we see these layers in the abalone shell. And the layers, layer after layer after layer. And over here on the right, you can see how light comes in and reflects off one layer, 2 layers, 3 layers, 10 layers, and all of these lights interfere, add together, and give you different colors at different angles. An amazing natural coloring. And so another ingredient that can be used to add shine or color to nail polish is fish scales. So if you have a nice reflective, glittery reflective nail polish, it probably came from fish scales. And what they do is they grind up the fish scales to produce tiny flakes, here shown in a scanning electron microscope, of layers alternating guanine and hypoxanthine. And they have 2 different indices of refraction. And these actually, in visible light, make little mirror-like flakes. And so if you have eyeshadow or nail polish, and it has a glittery, mirror-like colors, then you get, you probably have these flakes. Oh, yeah. So one question in the background is, what's the biological function of those layers? Well, it turns out if you have, those layers are really solid layers, the layer themselves. But in between the layers, there's more of a flexible something. It might be like an organic molecule that's flexible compared to the more crystalline layer itself. And that gives you the idea of layers of bulletproof material with cloth in between. So this is what makes the shell of the abalone so strong. And by the way, look at this nail polish. This had extremely small flakes, so you don't see the individual reflections, but on the whole, this nail polish looks very much like an abalone shell. So that means they've got the flakes really fine and really layered. It's totally amazing what they're doing. Ariana, yes, so this lecture is recorded by the Science Circle and available next week on video on their website, and also all my slides will be available. But you can also emphasize the individual flakies in these layers and do something called holographic nail polish. So, for example, here, look at all the flakes here, each one at a different angle to you, and they reflect different colors of light. And these layers are also made usually with mica, and it's coated with titanium dioxide. So nice inert ingredients, even though they look amazing. You can also make holographic effects, like we do with a compact disc. So a compact disc, as you might know, has a spiral of pits in it. And these pits are spaced a little more than a wavelength of light apart, 1.6 micrometers, 1600 nanometers. And that the rows and rows and rows of pits behave like something called the diffraction grating. And so you get this metallic surface that has these colors reflected from it, no pigment at all. And they've come out with coatings for cars now that have a diffraction coating. And I'm just waiting for a nail polish to come out that uses the same effect. Although I know how to make it myself now, because I actually do peel the coatings from compact discs to make them clear, at which time they act like a diffraction grating. And I've always thrown away the peelings, but I bet I can take the aluminized coating from a compact disc and adhere it to my nail and make some amazing nail polish myself. By the way, your nails grow at the same rate that the continents drift, about 1 to 20 centimeters per year. And at the Exploratorium, we featured a continental drift manicure. We had a specialist come and would paint a thin line or put a thin decal on your nail, and you could keep that on manicure after manicure and watch your nails grow at the same speed that the continents drifted. By the way, there are now water-based nail polishes. The water itself evaporates, some penetrates the nail. This is really staining. So the ingredients are water and a styrene acrylate copolymer and an acrylate copolymer. And this is sold for Muslim women that cannot coat their nails with material that doesn't let water come through it. This is water transparent nail polish, but it is hard to get off. If you ever saw the movie Holes, you know that Sigourney Weaver, as the evil head of the prison camp, used rattlesnake venom in her nail polish, and I don't think that's a good thing to do, but it's probably not too bad. Other chemicals in nail polish, that should say toxic in high doses, not oxic, dibutyl phthalate, formaldehyde, and toluene, but for the actual user, the actual amount of these chemicals that you encounter in nail polish is way below the safety level. I mean, it's just sub level. The thing you might worry about is people who work in nail salons that get exposed to this 8 hours a day, every day. So these chemicals have slowly gone out of nail polishes. Dibutyl phthalate, the plasticizer, formaldehyde as a nail hardener, not good for you anyway, and toluene as a solvent. And this is the last slide, just in time. So next time you're at the salon and trying to decide what kind of nail polish you want, just think gun cotton or bone cement. Your dentist uses probably ultraviolet cured polymers, which are the origin of the ultraviolet cured polymers in nail polish, actually. Do you want fish scales or coated mica for the effect? Do you want staining or non-staining pigments? And do you want to emphasize chemistry or physics? So that brings us to the end of the lecture. And thanks again to Science Circle, and I hope you learned a lot and had a good time, and I'm glad to see some men in the audience. Chemists, too. Oh, yeah. So indeed, they actually do have a nail polish that responds with a color change if there's a date rape drug in your drink. Um, so that's really an interesting thing. And it turns out that one of the tests for date rape drug is actually triggered by Dr. Bronner's soap. So you have to watch out a little bit if someone's trying to slip you a Mickey with Dr. Bronner's soap. It'll show up on the nail polish. Yeah, I wondered how interested this would be to the full audience. Uh, yeah, Mike, I haven't seen anything other than the radical based. I haven't seen the condensation polymers. The acrylics, the acrylic that mixes the solid form of the monomer with the hydrogen peroxide and activator. Um, those are radical based as well. But yeah, so hey, maybe Mike, there's a business here where you could make a condensation polymer nail polish. Yeah, yeah, they probably are very slow. Uh, Very slow to the condensation polymers. Oh yeah, and I'm not an expert in nail diseases, onychomycosis. Sorry, don't know about that. um, there are some good sources out there though, if you go online. Maybe on the final um, slide, I'll add in some of the resources I found for nail polish safety. Um, so, Ilsa, yes, there's a regular series of science talks here at the Science Circle, um, often every week, usually every month, and there are different topics. Maybe people from the Science Circle can give the link to the website where all of these are listed. Yeah, while I was researching this, I did find that the interference effect paint, like on the car or on the compact disc, they put that into clothing, and it looked amazing. I'll take. Yeah, I hate to go away, but let me check that. Let me check that dress. Oh, thank you for posting the. Oops, I couldn't look at the dress. Sorry. Let me see if I can go to that site that Private showed me. No, I can't go there yet. Okay, so any other last comments or questions? I really um, I really worried a little bit because I know this is be more interesting to the women, perhaps, but it was nice to have a nice mixed audience here. Great. Thanks, Mike. And I always come to yours when I can. And I certainly watch them afterwards. So that was good. Glad I didn't make too many chemistry errors. Oops, I may be crashing. Whew. I guess I'm not. Oh yeah, they actually do have color change that can be electrically stimulated for cars. So you can drive along in your car and apply a magnetic field to the car using electric currents and change the color of the car. Just amazing. And they, even do that with dresses. I'm not sure what's going on, but my Second Life is Firestorm is having a little trouble here. I'm not sure what's happening. Oh yeah, so there are many recorded lectures from the past from Science Circle. They've been recorded in machinima, videoed, and I make all my slides from all my talks available. Now, normally, I'm a physicist, and I have my minor was in planetary physics, and I've actually done research on Mars. So my usual lectures are about planetary physics. And of course, this week, with the final resting place of the Rosetta on Comet 67P, I'm going to have to do another lecture to wrap up all that we learned from the Rosetta mission. And I'll probably do that after the annual meeting of the American Geophysical Union in December. So maybe January next year, I'll do a lecture on everything we learned about comets and some of the wonderful images. Oh yeah, and the fact that they saw um, geyser-like plumes of water on Europa, which means that in our mission going to Europa to try to sample the ocean that's beneath the ice crust of Europa, we can sample it by flying a spacecraft through the plume and collecting material in the plume. And we've done that at one of the moons of Saturn, Enceladus. Enceladus also has geyser-like plumes that we've flown spacecraft through to study. And they actually did discover the final resting place of Philae. They found the lander, and there's some wonderful pictures of that. Yeah. So yeah, there'll be. I think they'll have some good lectures coming up, and I may have some time. In the next 2 weeks, I'm heading out to India. The Dalai Lama has hired the Exploratorium to be the science teachers for Tibetan monks. He believes that Tibetan monks should learn science, and so I'm going to teach the senior monks of Tibetan Buddhism about science, and they are the best students I've ever had. They really listen, and they love to argue, and they really want to learn. So motivation and intelligence and just really great people. So I'm going to have an exciting time, and I won't be in Second Life that much because their internet connections are slow. Yep, and I promised Chantal that I would give a presentation about, this will be my 4th trip to go to India to teach Tibetan monks about science. And what do you teach a Tibetan monk about science? What are the fundamental things about science that they need to know? And that's quite a big discussion that's evolved over time. Yeah, I get so many volunteers to go with me. It really is an amazing adventure. Okay, well, I'm going to sign off and let you get on to your Saturdays, and me too. It's really a pleasure to be here, and I will send off my slides, and they'll appear soon. And thank you all.